Hi, and welcome to this week's video where we are going to be introducing kinematics, which is very exciting because this is where physics can get applied. Because I feel like one of the hardest problems with physics is that a lot of people get intimidated by it, especially because it seems so far-fetched and irrelevant. But physics is actually applicable in almost every single aspect of our life. And kinematics is one of the greatest ways to get introduced to how we can see and learn about physics by applying it to things we see every day. So in this video, we're going to start off with talking about motion along a straight line, which is probably one of the simplest types of motion we will encounter. So what is motion? We're going to define kinematics as the classification and comparison of motions. And in this lesson, we're only going to be looking at straight line motion, but there are various types of motion. We can go into 2D motion, but we will go into that later. And here we will only consider particles and particle-like objects, which means that every part of the object moves in the same direction at the same rate. So as you can see here, the cube on the left would be considered a particle-like object. However, this tumbleweed would not be considered a particle-like object because, it has a lot of these branches sticking out and it probably wouldn't be moving at the same rate. Position and displacement are two very important values that we will be encountering a lot in the upcoming lessons, so it's good to get familiar with them. Position and displacement are sometimes used interchangeably, though they are not exactly the same thing, because position determines where your object is relative to a specific reference point. Also, notice how we say relative to a reference point, because we are able to define that reference point where we want. Usually, it's at the origin point of an axis. Say we have a simple x and y axis. Usually we would define this point as our origin at 0, 0, but that isn't always the case. So watch out where you define your reference point, as your position and displacements will work relative to that. And displacement, which we denote as delta x, is the change in position. Make sure you recognize this word change here, because a lot of people forget that it's the change in position. So you have to subtract your initial position from your final position. And make sure to watch your signs, because if your initial position was negative, let's say your final position is at 2 meters on the x-axis, and your initial position was at negative 3 meters. If you subtract negative 3 meters from 2 meters, you get 5 meters, not negative 1 meters. So make sure you watch out for your signs. And displacement is also a vector quantity, so there should technically be an arrow here. So it has both a magnitude and a direction. So for example, let's see on the running track on the right here. Let's say you start at this line over here. If you make a complete loop around, your distance might be, 400 meters usually? But your displacement would be 0 because you're at the same place where you started. So displacement is not the same as distance either. So now we're going to move into average velocity and speed. Average velocity involves a particle's displacement, and it is basically the rate of change of the particle's displacement. And how we write the equation for velocity, which is also a vector, notice the arrow above the v. So velocity, the average velocity, is defined as a change in displacement vector over the change in time. And here you can also see we have a bar above the v, so v bar will denote average velocity. And that is simply the change in the displacement vector. Notice the magnitude and the displacement vector, which has also a direction over the change in time. And the average speed just involves a particle's distance. Notice how we differentiate between displacement and distance here, because those are two different values. Remember, on the last slide, we just talked about how if you ran 400 meters on a lap on a track, you would have 400 meters as your distance, but you would have 0 meters as your displacement. So the average speed here is defined as the total distance traveled over the change in time. And if we look here on this graph, let's say we start over here and then we end up over here at 5 seconds. So this is 5 seconds, and let's just arbitrarily define this as 10 meters for simplicity. So the average speed, average speed in this case, let's just call it the average speed because we have S on our y-axis, which is going to be our distance. So the average speed here would just be the slope of the line that we draw between these 2 points. That wasn't a very good line, but if we take the slope of this line, it would just be 10 meters, the rise over the run, right? We've all learned that. So 10 meters over 5 seconds, and that would give us 2 meters per second. And notice how we get the meters per second unit from that. Now, what is the difference between average and instantaneous velocity? So average velocity is the velocity averaged over a certain number of time over a certain displacement. But here, we're going to measure how fast the particle moves at a given instant. Now, if we think about it, that's just like an average velocity, but the time is getting very close to 0. So here, what we do is we take the limit as the time approaches 0 of the average velocity. Now, the speed is just the magnitude of the velocity or the instantaneous velocity, which we'll call the instantaneous velocity because that's how we usually call it. And then we'll call the average velocity the average velocity. So for example, positive 5 meters per second and negative 5 meters per second are two different velocity values. However, they would both have a speed of 5 meters per second. And again, the units are in meters per second. Acceleration is just like another step above velocity. It's the rate of change of the velocity, whereas the velocity would be the rate of change of displacement. So the average acceleration, again, it is a vector. So it has both a magnitude and a direction. Let me just go and denote that. So it should be the change in the velocity vector over the change in time. And the instantaneous acceleration, similar to the instantaneous velocity, is just the average acceleration as the change in time approaches 0. So we're taking a very, very short, almost 0 seconds worth of a time interval, and then we're finding the acceleration of an object at that particular instant. Now see how we have denoted it in several different ways. So first is the denotation that we have seen before, or the expression we've seen before, where we take a limit as delta t goes to 0. But here we have something we haven't quite seen before. So dv over dt, that just basically means the rate of change of velocity. You can sort of think about the dv, the d and dv as the delta sign. So those are almost equivalent. And we just say that that is the rate of change of velocity. And you've taken calculus before, you would know this. And also, because velocity is the rate of change of displacement, we substituted that in there. So now we see that the acceleration is the second derivative of the displacement. If you don't quite understand that, that's okay. You could probably go back to calculus and do some revision for that. But it's a pretty basic concept once you understand it. Just remember a lot of rates of changes and how they're all related to each other. Now, we have a special case which is very helpful. However, notice that this only works with a constant acceleration. This is not valid. What I'm about to say is not valid when our acceleration is not constant. So always make sure that if you're going to use any of these following equations, that your acceleration is constant. But when your acceleration is constant, we have 5 very useful equations that we can use to solve kinematics problems. And we call those the big 5. And basically here we just have a velocity equation, which says that the final velocity is equal to the initial velocity plus the acceleration times the time. And in the next 2 equations here, we have displacement equations. How the displacement is related to the velocity and acceleration. There are certain derivations for that, and I'll be going over those in another video. But for now, just memorize these equations because it'll be very useful in any of the problems that you solve. Now we're going to talk about a special type of acceleration, which we call the freefall acceleration. So let's say you toss an object up or you toss an object down. It doesn't matter which way. And let's say we eliminate any effects of air during its flight, meaning we're not going to think about variables like air resistance or drag during its flight. On Earth, there is something called the freefall acceleration, which we represent as 9.8 meters per second squared. Now, freefall acceleration can exist anywhere, but on Earth specifically, locations near ground level or sea level, the freefall acceleration value is equal to 9.8 meters per second. And what is special about this is that it is independent of the object's characteristics, meaning regardless of the mass or the shape of the object, the freefall acceleration will be the same. So if I had an extremely large bowling ball or a small ball, think about Galileo's experiment on the Tower of Pisa, the value of the freefall acceleration, which we denote as g, would be the same for both of them. However, we should note that g does vary with latitude and elevation, as we'll see in a later lesson, especially when these elevations get rather extreme, like when you're going above Earth's surface, for example, and into space. And g, remember that g is 9.8 meters per second. G itself is not negative 9.8 meters per second. It only matters on the directions that we determine for the positive and negative axes. For example, if I had the y-axis here and I denoted the positive side of the y-axis as pointing to the top, then anything falling down would experience an acceleration of negative 9.8 meters per second, or negative g. But the sign depends on how we define our axes and the directions. So that is just a basic introduction to motion along a straight line, and I hope you learned something new. So come back and we will talk more about kinematics and the more complex natures of it.